What I'd like us to do is the last few sessions we've been working with logarithms and exponentials and trying to understand those fundamentals, including the various properties associated. But what we want to do today is we want to really focus on solving different types of equations where if we have an unknown exponent, we want to be able to solve those exponential equations to find out what that unknown exponent is. Or if we have a logarithm equation where there's unknowns built into those logarithm portions of the equation, we want to be able to solve for those unknowns. And then start looking pretty carefully at applications. So this session and the next couple sessions are going to address mostly applications using our skills to be able to handle both exponential and logarithm type of problems. So first of all, the question was asked from someone from homework here, and it was to sort of collapse a logarithm expression. And let me go ahead and put it up here. This is not an equation. This is an expression. And this one happens to be from our textbook on page 305, number 63. It says collapse 2 log base 2 of x plus 1 minus log base 2 of x plus 3 minus log base 2 of x minus 1. You can just see we have a sum and difference of logarithms here, and all we want to do is collapse this into a single logarithm. We need to know how to do this so that if this was, say, equal to something, turn it into an equation where it was equal to something, we need to always isolate the logarithm first, and then we go through the solution technique. So we need to learn how to make sure that we can collapse this into a single logarithm. So it was a good question to start out with today. So there are several properties that we've learned already. When you see something out in front of a logarithm, then what can we do with this something, this 2 in this case? You can bring it back in, and that rule is your power rule, isn't it? It comes back in here as the exponent on this binomial expression. So this becomes the log base 2 of x plus 1 being squared. That first one. Now these others are subtracted from this logarithm. There was a quotient rule that said if you have a logarithm of a fraction, a numerator and a denominator, then that's going to split into the logarithm of the numerator minus the logarithm of the denominator. So in reverse, if you see here's something minus these logarithms, then what's going to happen? What's going to happen to these two logarithms? Here's a hint. I put a fraction bar here.
So does the x plus 3 go under that, and then there's another fraction bar?
No.
Or they both go on the bottom?
Imagine this. Actually, let's play this game. They do both go on the bottom, to answer Melissa's question. They will both go right down here, but let's sort of see why. If I took and factored this negative out in front of this, this would leave the log base 2 of x plus 3 plus the log base 2 of x minus 1. Now, these two logarithms are added together, right? Those two logarithms are added together if I pull this negative, this subtraction here, out in front. So those logarithms are added together. Now we know what property? The product rule. The product rule. If you have a sum of logarithms, that's going to collapse into the log of the product of x plus 3 and x minus 1. See how this becomes that, and then this negative sign, subtraction, is out in front of this. So we now have this logarithm minus that logarithm, so that drops the x plus 3 factor and the x minus 1 factor down here. And this is all inside that logarithm. Okay? That's what Diana's question was about, with how to collapse this. Any question, any confusion there?
Should you multiply those things out or
No.
simplify it?
No, I'd leave them this way. I'd leave them this way. Okay. Now, rather than just believing me, why would you probably want to leave it this way?
You're gonna end up factoring it again if you've got an equation.
Yeah, if you're trying to do something with this mess, if you're trying to do something with this, then you're going to probably want to keep it in this format initially, anyhow. Okay.
So what happens with the minus log squared?
Right here?
You know, up above where you factored it? Can you pull the negative sign out?
I just factored out the negative here. Yes, so I'm subtracting now the sum of those logs.
Oh,
The sum. But if you see a sum of logarithms, that becomes the log of the product. The sum of logs becomes the log of the product. That's your product rule. Yeah. Jerome?
I forgot about the product rule, but I got the same answer.
Sure.
Okay.
Yeah, because you're subtracting. So that means when you're subtracting a logarithm, then that means that this argument here, in math they use the word argument for an expression, essentially. And so when you're subtracting logarithm with this argument here, this binomial, then that just sticks this thing in the denominator. Similarly here.
No, I mean, what I did was x plus 1 squared over x plus 3, and then another division line, x minus 1, and then I multiplied it out, so I got x plus 3 times x minus 1.
Same thing as this, though?
Yeah.
Yes. Yeah.
Okay. So,
Yeah. So there's different ways you can kind of work your way into it. All right? Why not? Why don't we take and make this into an equation now, since we're already off to a good start? Let's say that this problem, instead of being an expression, which was this mess we started with, let's say this was equal to something. And we're asking the question then, okay, so let's turn it into an equation. Okay, so we now have a complete sentence here, equals, and let's make this say equal to 3. Make it simple. So we have a complete sentence. So here is the equation. What are we trying to solve for?
X.
Yeah, very good. Okay. You look at this mess and you go, okay, I have a logarithm equation because it's a complete sentence, and the unknown in here is x, and the question is, what value of x could you put in there that'll make this mess over here equal to 3? Okay? Just like beginning algebra. If you have an unknown you see there in an equation, no matter what style of equation, there's a certain technique for that type of equation. So the technique for solving a log equation is to isolate, I've said this before, but I want to reiterate it, isolate the log. So here it's been isolated, it's equal to 3, and now how do you solve that? The first step is isolate the logarithm, which we've got. How do you now solve a logarithmic equation? Yeah, Taylor said put it in exponential form. So the logarithm, remember, is an exponent. You've got this exponent equal to 3. The base is sitting right here, it's a 2. So what would you write, Taylor? Want to help me?
2 is a third,
Right on.
and then equals
equals this algebraic or this rational expression here. X plus 1 squared over x plus 3 times x minus 1. Okay? Now we're back to almost an intermediate, actually it is an intermediate algebra question. Not too tough once you get it back to this format. So let's keep on going. So when you see now a fractional equation, what's your technique you use with a fractional equation? I keep repeating myself to the point of putting you to sleep almost. You clear the fractions out of the fractional equation. So you multiply both sides by the common denominator, which happens to be this product down here. Multiply both sides by that. So next step is that we get x plus 1 squared is equal to 2 cubed is 8. 8 times x plus 3 times x minus 1. And we should be pretty quick multiplying that out. That's x squared, inside, outside is 2x, and the tail end term's negative 3. So we get x squared plus 2x minus 3. The problem started out as a logarithmic equation. We transformed it into an exponent or a fractional equation by writing this equation, and then we cleared the fractions. We now have a quadratic equation, which is a good review because quadratics never disappear as long as you're taking math courses or science courses. So what we get is x squared plus 2x plus 1 equals 8x squared plus 16x minus 24. We now move everything over to one side because we see this as a quadratic equation. So I always try to keep my leading term positive. So I would imagine x squared being subtracted from both sides. So I get 7x squared, bring the 2x over and get 14x. Check my math, make sure I don't screw it up. And then I subtract 1 from both sides, minus 25. That equals 0. A quadratic equation. Is that factorable?
Why don't you just use the quadratic?
It's probably not factorable.
Look,
Probably not. So what I would do is I would just use the quadratic formula. Use your brain, not your calculator. Okay, first brain and then calculator. So let's go over onto the other board so I don't have to bend down here. And let's write down our quadratic equation. A quick review because everybody gets rusty on this. Here's the problem. This is of the structural form ax squared plus bx plus c equals 0. The solutions to that style of an equation is, or happen to be, minus b plus or minus the square root of b squared minus 4ac all over 2a, and everyone should have that, know that as well as you know your phone number. And so you drop in the various numbers. So the opposite of the linear terms coefficient is negative 14, plus or minus the square root of 14 squared is 196? 196? How did I know that? Okay. Minus, now here's the trick. When you use do the quadratic formula, people usually screw up the arithmetic right here, b squared minus 4ac. Have you all done that incorrectly before? Most people have. What I usually do to not make the mistake myself is I know I have a negative 4 times a times c. So I first of all get the plus or minus sign right there. If I have a negative times a negative, I know that's going to now turn positive. Now all I worry about are the numbers. 4 times c is 100 times 7 is 700. So I'm adding 700 to the 196. All over 2a is 14. So then let's keep on going. negative 14 plus or minus the square root of 896 all over 14. Now, does 896 clean up in the sense of being able to pull some perfect squares out of there and simplifying that radical, if you wanted the exact answers? If you wanted the exact answers. So what I would do at that point is I would use my calculator, or if I felt like entertaining myself with a little arithmetic, I know this is even, and I could start dividing it out to try to factor it down to see if I have any perfect squares in it. So let's go grab the calculator for a second and see what we can do with 896.